Good morning, everyone. Welcome to One Problem Per Day portal. And this week, we are going to explore problems on electricity. So, that is from the date starting from 5th of Jan to 10th of Jan. The series of 5 problems. This is both for IB1 and IB2. Okay, so both of you can use it. Okay, now let us start with this first problem. This will be published tomorrow, that is on 5th Jan. Okay, so this problem is considered to be one of the easiest problems that I have seen so far, and this is for 5 marks. So I have put the time limit as 5 minutes. Let me start the timer. Right. Okay, so two cells of negligible internal resistance are connected in a circuit. The circuit diagram is shown over here. There's a 12-volt battery, 2-ohm battery, and a 4-ohm resistor here. The top cell has an EMF of 12 volt. EMF as EMF of the lower cell is unknown, and the ideal ammeter reads 0 current. Okay, calculate the EMF of the lower cell. So he is asking you to find out the EMF here. Now, when you say it reads 0 current, which means what? No current is either entering here or it's exiting from here, right? So therefore, this appears to be that this circuit is so totally seen to be detached from the full circuit. So whatever current is being taken from the 12-volt battery, all the current flows only through this primary circuit. It does not enter the secondary circuit over here, right? So therefore, what is the current passing through it? Let us estimate. So this would be 12 divided by 2 plus 4 will be your current. Why? Because it's in a series circuit over here. You are not going to consider the circuit because no current is passing through it. So 12 divided by 2 plus 4 is 6, which should be 12 by 6, which should be equal to 2 amperes. So 2 amperes is the current passing through it. So here 2 amperes, here also 2 amperes over here. Now what is the voltage drop across this? In this case, this should be voltage drop here should be 2 multiplied by 4. V equal to I into R, which should be equal to 8 volt. Now you see, if it is 8 volt over here, and if no current is passing through it, then the same voltage should also get dropped over here, because if there is no electric current here, you need not consider this. So the EMF of the cell is also equal to 8 volt, right? So your answer should be 8 volt over here. 8 volt. Okay. Now let us move on to the next one. Now here it says, second part B, it says the diagram shows charge carriers moving at speed v in a metallic conductor of width L. Okay, so the width L, the charge carriers, he has not told you whether it's positive charge, negative charge, just charge carriers. We will assume this as positive charges. Okay, the conductor is exposed to a uniform magnetic field and is directed into the page. Okay, so you have a magnetic field like this, and you observe that these charge carriers are moving straight. Now, can this be possible? Now, let us understand this problem much more clear. So now what is happening is, when you have a magnetic field directed like this, use my FBI rule, that is your left hand rule of Fleming. So if B is like this, the current is shown by the middle finger, it is shown like this over here, and then where should the force be? Force should be acting like this. That means these charge carriers, if they are positive, you should expect them to go like this. If they are positive, I put a clause here saying that if they are positive, then they should get attracted here. But what's happening over here? They are not getting attracted. But still it's charge carriers, which means already there are a lot of charges over here. There are already a lot of charges over here, right? So as a result of it, these charges are now repelling over here. So as a result of it, you expect these charges should move downwards. So if that is the case, okay, so it should, so this is your FB force, and this is nothing but your repulsive force, and as a result of it, it's going straight away like this. Okay, now what is being asked? We need not read the full question. Show that the potential difference established is across the conductor is given by capital V equal to VBL. Okay, potential difference. Now, when you say there is a potential difference, what do you mean by that? There should be an electric field. Okay, now we already written the positive charges over here, which means what? The electric field should originate and should be like this over here. It should be like this over here. So if like this over here, then what will happen to these charges? So magnetic forces are now pushing the charge like this. The electric force is pushing the charge like this over here, downwards. Which means if they have to go straight, that means the electric force should be equal to the magnetic force. So that the net force acting on it is 0, right? So let me write it down here. So this will be, if I draw the free body diagram, I can write FE is acting downwards, FB is acting upwards. So these two are balancing each other, and hence the particle is going straight. Okay. With this clue, what we'll do is we'll start writing this. FB is equal to FE. What is FB? QVB sine theta is equal to, what is FE? Q into E. Why didn't I write sine theta here? Because theta equal to 90 degrees. Why 90? Because you know, this is the magnetic field, this is the velocity vector. The angle between the velocity and the magnetic field vector is nothing but 90 degree. They are perpendicular to each other. Okay. Next, So therefore, using this, now I can cancel this Q and Q, and I will be able to write V into B is equal to capital E. Now what is E here? E is the electric field. But what is that I have? Do I have electric field? No. I have the potential difference and then the length between the plates. Okay. So therefore, so V divided by L is nothing but electric field. You remember this question, this particular formula, which is nothing but potential difference divided by distance. You have studied something like V by X is equal to E. I have done the same thing. X is nothing but length over here, and thus you can now write, you can substitute this over here. I'll write this capital V divided by L is equal to so much, or this implies capital V is equal to VB into capital L. So as desired, whatever we require, we have got this one, right? So this is a standard derivation that you would have studied in your textbooks, right? Then on the diagram, label the part of the conductor where negative charge accumulates. Now, if positive charge is getting accumulated here, negative charges should have been here. Why should I say that? The reason is because there is an uniform electric field which is directed downwards. The electric field is directed downwards, so negative charge should be on the lower plate, right? So this for 1 mark. And okay, so with this we come to an end to this particular question. Let us move on to the next question.